Okay, here we are back at it. It's going to be great. So, I'm continuing my series of numerical calculations. In the last episode, I'm going to show you it to you in just a second. Actually, let me show you that too. So, here's the last episode was this. Okay, this shows a satellite orbiting the Earth. You can't really see it because see, there you go. So that's what we did. So go back and watch that video if you want. This is where I'm starting from. So what I want to do is change this satellite into the moon. So suppose I have the Earth right here and the moon right there. What's different about the moon than a satellite? And the answer is this right here. The moon has a mass of 7.348 times 10 to the 22nd kilograms. So it's a significant mass. And so we can't ignore the influence of the moon on the Earth. So we really have two objects moving now. So we have the one we had before, which is the gravitational force on the moon and the change in momentum of the moon. But now we also have a gravitational force on the moon and the Earth, and a change in mass of the Earth, change in momentum of the Earth. Okay. So here is what we're going to do. We're going to calculate this gravitational force, which I already did in the last episode. But now I just have to have that same force but opposite value on the Earth. And then I need to update the momentum of the Earth. So it should be straightforward. So here's what we're going to do. Just like before, calculate r, the vector position from the moon to the Earth. 2, calculate the force. We did that too. 3, update the momentum for the moon. And update the momentum for the Earth. And then update the position for both of them. So that's what we're going to have to do differently. Now up here I put some data because I forget the mass of the moon, the radius of the moon, the Earth-Moon distance, and this down here is useful. This is the speed you need to move in a circle, in a circular orbit. I didn't tell you where that came from, but I will show you later. Okay, so I need that information. Let's go back over to our program and start calculating stuff. And I apologize, I should have put this window, it's not so bad. There. Okay, so the first thing I'm going to do is add in this other data that I just put over here, just so I have it. Okay, so I need the mass of the moon is 7.348e22. The radius of the moon is 1.7371e6. And then REM, I'll call it the radius, the distance, 384.4e6. I think that's all I need. Yeah. Okay, so now let's get rid of this. And you're going to see something really cool here. Moon equals sphere. Position equals... Okay, so I want it to be in the x direction. Then I want it to be, let's say, how about we do this? Earth.pos plus the vector REM 0, 0. So that's going to take wherever the Earth is and add on to this other position right here. So it's the correct distance away. Because remember, I didn't put the Earth at the origin. The radius of this is going to be RM, and I'm going to leave it as gray. Let's make sure we have make trail equals true. Okay, now I can go down here and I'll say moon.m equals moon's mass. Moon.momentum is moon.m times vector. Let's just put the 0, 0, 0 for right now. Everything else is okay. Down here, I need to change this from moon, 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 and moon. Okay, now I need to also, this is the gravitational force on the moon. So I use that to update the momentum of the moon. I need to now update the momentum of the Earth. Earth.p equals Earth.p minus F times gt. So really it'd be plus the force on that, but it's negative F, so I'm just going to say minus F. And then I need to update the position of the Earth. Earth.pos equals Earth.pos plus Earth.p times dt divided by Earth.m. I think that's good. Oh, I need to do this. I didn't do this. I am editing all this stuff. Copy. So let's say copy. Okay, good. Save. And we'll call this, you can't see it up here, but I'm going to call this Earth Moon System. Are you ready to run this sucker? Something cool is going to happen. Look at that. That's the cool part right there. Look at that. There's the Earth, there's the moon, everything's to scale. And it shows you how far apart these things are. I mean, it's just hugely far apart. Okay, let's put this back at 10, move it back 10, just so it fits a little bit better on the screen. See, look, you can barely see the moon. Everyone thinks the moon's so close, but it's not very close. Textbooks draw this wrong because it just looks bad. So they draw it differently. But let's leave it, because we don't have to have it look good. We want it to be good, right? So it is running, but you just don't see anything. Okay, things are just happening too slow. So let's just, let's put dt at an hour. So that's 3,600 seconds. And then let's run this for, a month. So a month, let's see, month equals 28 times 24 times 3,600. So that's 3,600 seconds per hour, 24 hours, 28 days. So that's while t is less than month. You like that? Let's see what happens. Not much there, huh? Let's speed this up to, I would think something should happen. Aha! That's right, nothing happened. I missed one. Okay, that was my fault. Okay, so bad things happened. So let's make this, let's just make that time step a little bit smaller. Okay, there. So it goes through the moon, through the Earth, because I didn't give it the right starting velocity. So let's go back up here and let's say this same R calculation right here. Okay, now I can say the velocity, let's give v start equals square root g times the mass of the Earth divided by the magnitude of r. That's what I said. And then put this at v start. Let's see if that works. Yep, there, look. Circular orbit. And it should take about 28 days to go all the way around. Now you're going to notice something. Look. Let me run that a little bit more. Let me run that a little bit faster, say twice the speed, and for 4 months. So it goes around. It doesn't meet back on its own orbit. Is that weird? Look at that. You know why? Because the Earth is moving too. Okay, so in this case, I'm updating the position of the Earth so it also moves, because the momentum of the whole system is not zero, because the Earth was at rest and the moon was moving up. I can fix this, right? I can make the momentum of the center of mass zero. Watch this. Okay. So if I give this, I'm going to go down here. There's my momentum of the moon. I'm going to Earth.p equals negative moon.p. Now let's run it. Now it's a perfectly circle. See, and the Earth is moving. See it? It's moving in a circle. It is indeed moving. Okay, let's do something cool. How about we plot the momentum? T graph equals graph. X tidal equals time. Y tidal equals X momentum in kilograms meters per second. And then Fm equals G curve, let's say Fe. That's the plot for the Earth. G curve color equals color dot blue. Label equals Earth. Fm equals G curve. I'll just leave this one as black. It's the moon. But I'll give it a label. Moon. Now go down here. And I'm going to plot Fe.plot T Earth.P.x. Fm.plot T moon.P.x. So I'm going to plot the x and x momentums of the two things. Let's run it. Check that out. So the total momentum is 0, you see, and as the momentum of the Earth increases in the x direction, the other one decreases in the x direction. The total momentum stays constant because there's no external force. Any changes in momentum of the Earth are compensated by the change in momentum of the moon because they have the opposite forces on them for the same amount of time. What do you think about that? This is one way that we can check to make sure our model is working. Okay, I'm going to stop it there, and I will link the code below, and there you go. Have fun with that.